Okay, so let's pick up where we left off with implicit differentiation, and let's look at a couple more examples of finding the derivative using implicit differentiation. So remember, what we're going to do for these particular examples when we apply implicit differentiation is we're going to be thinking of y as a function of x, even though we maybe can't write it that way. And clearly on this one, this would be a very difficult task to figure out how to write y in pieces as a function of x so that we wouldn't have overlaps. And that's not something we want to do. So we want to use implicit differentiation here. We're going to take the derivative of both sides of this equation with respect to x. And we're going to be thinking, whenever I differentiate with respect to y, we're going to be thinking as y is a function of x, and we're going to apply, when we do that, we will apply chain rule appropriately. So apply chain rule, okay, when differentiating y. Okay, so that's kind of our very generalization. On the first video, I went through a lot of steps, but that's our idea right there. Now, when I come across this first term, it's x times y, and so I'm going to have to apply product rule here as I differentiate this. So we'll go ahead and do that. So when I take the derivative of x, I get 1 times the sine of y plus, then I'm going to take the derivative of the sine of y. Well, the derivative of the sine of y is the cosine of y. But since I'm differentiating y, I have to think, right? Like if I had the cosine of a function, then I would have to take the derivative of that function, that inner function, right? If I was applying the chain rule. So this is going to be dy dx. And then we have to multiply by the x because we're in the midst of a product rule. Okay? So remembering that we have to, right, whenever we differentiate a function with y in it, like sine of y, we have to remember that we apply the chain rule because we're thinking of y as a function of x. So we have to multiply by the rate of change of y with respect to x every time we take the derivative of y. Okay, then we keep going. Then we're going to add. Get this all on the same screen. Then we're going to have to add the derivative of the cosine of 2y. So the derivative of the cosine is negative sine of 2y. But then we have to take the derivative of 2y, and the derivative of 2y is 2. Then we have to take the derivative of y, and the derivative of y is dy dx. And let me pause this and scoot it down so I have an. So again, remembering as we do this, right, that we're having to apply the chain rule. Since we're taking the derivative of y, and y is a function of x, we have to multiply by the rate of change of y with respect to x, dy dx. I use dy dx. If you like y prime, you can use y prime. The reason I use dy dx is so that the y prime doesn't get lost with the y's. The primes are easy to lose in a big notation. So now on the other side, we're taking the derivative of the cosine of just y. So again, the derivative of cosine is negative sine of y, but then we have to multiply by dy dx, the rate of change of y with respect to x. Okay? So all of these places, right, we were remembering that y is a function of x for each of those pieces. Okay, now we've actually taken the derivative, but now we have to find dy dx. So let's simplify a little bit here. There's not much to do, but this is the sine of y plus x times the cosine of y. And I'm going to drop those parentheses. Cosine of y times dy dx. And then we've got minus 2 sine of 2y dy dx equals negative sine of y dy dx. Okay, now the only thing left to do is to collect all my terms with dy dx in them, factor that out, and everything else on the other side. So what I'm going to do is I'm going to add the sine of y dy and subtract the sine of y. And let's do that. So we're going to end up, and I'm going to factor. I'm going to do multiple things at once. I'm going to pull out the dy dx from the terms x cosine of y minus 2 sine of 2y. since this is going that direction and that's going that direction, it's going to be a plus sign of y over here, plus sign of y dy dx, but I'm going to factor out the dy dx, and then on the other side we have minus sign of y. So I know, so I subtracted the sign of y, subtracted the sign of y, and added the sine y dy dx, and added to this side sine of y dy dx. And then I factored out the dy dx, and on the other side, all that was left on that side was just minus sine of y. So just kind of showing I did some of those steps in my head, so I showed them in red what I was doing in my head, and then I factored out the dy dx. Okay, now all that's left to do is just to solve for dy dx, which is just simply divide by that entire expression, minus sine of y over x cosine of y minus sine two sine of 2y plus the sine of y. And there we go. There's my answer. And now if I were to want to use that derivative, I could use it to find slopes of tangent lines and so forth. All right, let's do one more example. This time, let's actually, once we find the derivative, let's use it to find the tangent line to the curve at a specific point. And then we'll even go into Desmos and take a look at what this curve looks like, and I'll show you a nice little coding that we can do in Desmos so that we can actually see what these curves look like and even what the equations of the tangent lines look like. So before we do that, though, if we want the equation of the tangent line, we've got to find dy dx so that we can find the slope of the tangent line. So this is a case where I see that I could take the, I could solve for y explicitly as a function of x, but it would give me two parts because I would end up with a plus and a minus when I take the square root. And so rather than doing that, I can see that it would be fairly easy to simply take the derivative of this equation with respect to x on both sides and do so implicitly so that I can end up with dy dx implicitly defined in terms of x and y. So let's do that. So we'll take the derivative of both sides. Again, when we do implicit differentiation, we always remember that y is a function of x. So when I'm taking the derivative of y, like in this case, I have to apply the chain rule. So I get 2y, but then 2y to the first. But then I have to also take the derivative of y, or multiply by the rate of change of y with respect to x. So dy dx. And then on this side, I get 3x squared plus 6x, just simply taking the derivatives of those two terms with respect to x. And then dy dx is 3x squared plus 6x all over 2y. Okay? And so there's my derivative, and now I can use my derivative to find the slope of the tangent line and then take it further to find the equation of the tangent line. So now let's find the equation of the tangent line at 1, -2. So the first thing we need to do is find the slope, and so the slope of the tangent line is going to be dy dx evaluated at not just an x value, but evaluated at the ordered pair 1, -2. So when I plug that in, 3 times 1 squared plus 6 times 1 all over 2 times -2, I end up with 9 over -4, or -9/4 for my slope. And then the actual equation, y minus a -2 equals -9/4 times x minus 1. So y plus 2 equals -9/4 x plus 9/4, and then we'll subtract 2. And we'll find that y is equal to -9/4 x. Let's see, that would be 8/4, so 1/4. And so the equation of my tangent line, -9/4 x plus 1/4. And there's our final answer. And look at how nice that was, right? Like we didn't have to work with square roots and two pieces of square roots and figuring out which piece is which. We were able to simply use the implicit differentiation process to find dy dx. And now, of course, it is implicitly defined in terms of x and y, but that's okay because we can use that to find our slope of our tangent line and then follow up with the equation of the tangent line. So now I want to pop over into Desmos and I want to just show you how we can actually, if we know what this derivative is, I want to just show you a nice little way that we can actually see both the graph and we can show the tangent lines to a curve that isn't written as a function, that's written implicitly in terms of x and y. Okay, so here we are in Desmos, and I just want to show you that we can actually type in this curve that we're working with. So I just came over here while the video was paused. I typed it in right here, and I will share out this coding for you in the Canvas shell. But I just typed in the equation we were working with, which was y squared equals x cubed plus 3x squared. And you can see over here that it's created this curvature with this loop in it, right, which is clearly not a function, right? We would have to split it and look at each of the square roots, the positive square root and the negative square root of y if we wanted to do it explicitly as y is a function of x. And so then if we right here type in what we just found for our derivative for dy dx. So if I type in here, and I'm going to start with a division bar. So I have a fraction, so if I've got 3, so if I just type in 3x squared, and this is what we did earlier when we were in the notebook, so 6x over 2y. What that does is that creates my derivative. So this little f of x is dy dx, so implicit differentiation, and it is a function of x and y. That's why we had to write it this way, f of x and y. And then notice down here that we can actually change our a value. So right now a is not even on the curve, but the point that we wanted to look at it at was 1. So if I drag a over, we wanted to look at it at 1, -2. So if I drag a over to 1 and b over to -2, we will see right there that we actually have that slope of that tangent line. So remember, the equation that we had come up with is on the notebook, and I don't have that right now, but what we can see is we can see right there that we actually have our tangent line graphed to the curve, and we did all of that without ever having to express this function explicitly as a function of x, y is a function of x. We could even, if we wanted to at this point, if we wanted to know what that slope is, we could use, Desmos allows us to use function notation, and it was 1, -2. And so the slope is coming out right there as -2.25. We had written it in fraction form, -9/4. So this is just kind of a nice little application of what we're doing graphically. So we can see it in Desmos, we can see the curve, and we can see the equation of the tangent line. We have to type in those things, right? You have to find your dy dx to be able to type it in, and you type in the curve that you're working with here. Let's do another example. Let's take a look at this lemniscate. 2 times the quantity x squared plus y squared squared equals 25 x squared minus y squared. And let's find the tangent line to this curve at 3, 1. So once again, we're in a place where trying to solve for y explicitly as a function of x would be troublesome. Let's just leave it that way. It would be troublesome, and it would involve breaking this up into pieces and looking at a bunch of different little pieces. And that's not a road we're going to head down. So instead, especially not now that we know how to differentiate implicitly. So let's get in here and let's take the derivative of this, 2x squared plus y squared quantity squared equals 25 times x squared minus y squared. And you know what, let's go ahead and do here, just so that we have that 25 distributed, 25 x squared minus 25 y squared. And let's take the derivative of both sides of this equation with respect to x. And in doing so, we will treat y as a function of x, and we will apply chain rule when we're taking the derivative of y, as we've done on the last few examples now. So a couple of things. One thing is this is a nested function. So as I take this derivative, I have to peel away the layers using chain rule. So as I take this derivative, I'm going to end up getting 2 times x squared plus y squared to the first power. So taking the derivative of the outer function being that power squared. So this will of course become 4, but I'm writing it out in all the steps here. Then I take the derivative of the inner function, and the derivative of the inner function is 2x plus 2y times dy dx, because every time I take the derivative of y, I'm thinking, oh, that's really a function of x, so I have to multiply by the rate of change of y with respect to x, dy dx. Now on the other side of the equation, I'm going to have 50x minus 50y dy dx. Okay. Now I'm going to continue to simplify this out a little bit. I see that 4 right there, and I'm going to go ahead and distribute it within the x squared plus y squared, just because I need to get this simplified. So 4x squared plus 4y squared times 2x plus 2y dy dx. We'll go ahead and expand that out. I'm going to leave the other side for just a second, and then I'll carry it down. Expanding that out, I'm going to get 8x cubed plus 8x squared y dy dx plus 8y squared x plus 8y cubed dy dx equals, and carry that down, 50x minus 50y dy dx. And now I'm going to go ahead and bring all of, I see a little bit of simplification right now. We could reduce everything by 2. We probably should have done that maybe up on the top line, but before I did all the distribution, but I didn't catch it till just now. So why don't we bring all the terms that have a dy dx to one side. So let's bring this 50 over and factor that out, and bring these terms that do not have the dy dx to the other side. So we'll subtract those two terms to the other side where the 50x is. We'll add the 50y dy dx. So I'm going to do a couple things at once here. I'm going to write 8x squared y plus 8y cubed plus 50y. And all of those terms had a dy dx in them, so I'm going to factor that out as well. Okay. And then I'm going to move the 8x cubed and the 8y squared x to this side through subtraction. So on this side, we're going to have 50x minus 8x cubed minus 8y squared x. And now I'm going to go ahead and reduce each of these terms, because I could divide both sides by 2, and I'm going to reduce each of these terms by 2. So I'm going to make these 4. It's just going to make it work with a little bit smaller numbers, a little nicer. 25, 4, and 4. Now I'm going to divide both sides, isolate my dy dx, so that my derivative, dy dx, is equal to 25x minus 4x cubed minus 4y squared x over 4x squared y plus 4y cubed plus 25y. Okay, now that wasn't all we were asked to find. We were actually asked to find the actual equation of the tangent line at a point. So now we need the tangent line at 3, 1. And we're going to go to Desmos with this guy too and take a look and see what it looks like. So let's take this now and write the equation of the tangent line. So we've got dy dx, and now we just need to find the equation of the tangent line at the point, it was 3, positive 1, I think, yeah, 3, 1. And so we're just going to plug this in. So the slope of the tangent line, dy dx, evaluated at 3, 1, is going to be 25 times 3 minus 4 times 3 cubed minus 4 times 1 squared times 3, 4 times 3 squared times 1 plus 4 times 1 cubed plus 25 times 1. So we got 75 minus 4 times 27, 108 minus 12 over 4 times 9, 36 plus 4 plus 25. And we end up with negative 45 over 65. And negative 45 over 65, obviously that's going to reduce, so we've got our negative 9 over 13 as our slope. So we have negative 9 over 13. So once we get negative 9 over 13, that's the slope. Now all we have to do is plug that in to write the equation. So y equals, well, we're going through 3, 1, so I'll use point slope. Y minus 1 equals negative 9 over 13 times x minus 3. So y is negative 9 over 13x plus 27 over 13 plus 1, or 13 over 13. And y equals negative 9 over 13x plus 40 over 13 as the equation of the tangent line. And I'm going to pause. I'm going to go back over to that little code that we have set up over in Desmos where we can actually see this graph and we can even type in our derivative. So let's take a look at that like we did on the last one, just so that we can actually see, because these, what's fun about these curves that aren't written as functions, I mean, functions are beautiful too, but what's fun about these curves is we get these loops and we can get some really cool curvature and the loops and so forth. So let's go take a look at this lemniscate over in Desmos and the equation of the tangent line. Okay, so here we are. I popped over just into Desmos, into that same code we were looking at earlier in the video, although I have typed in the equation that we're working with here for this lemniscate. And so here you can see this cool little infinity-like symbol that creates. And we already came up with the actual slope of, or dy dx to represent the slope of the tangent line. So I called it m of xy here, and if we were to type that in right now, so I'm going to go ahead and type that in here, which we came up with just from the other screen from the notebook where we did the work. It was 25x minus 4x cubed minus 4 y squared x. And on the bottom, we had 4x squared y plus 4y cubed plus 25y. And then I wrote the equation down here, and that gives me the value of the slope. And what we can do here is, remember, the point that we were looking at it was at 3, 1. So if I drag this over and I get it, actually get that equation, that line, up onto my graph at 3, that right there, 3, 1, we're almost there, At 3, 1, we can see that tangent line right on the curve, right at that point. And so you can see that happening. And what we could do is we could adjust, and we could look at other points on the curve. I even wrote in what the slope of the tangent line was here. I forget, I didn't write that down. Oh, it was negative 9/13 is what we had gotten. So we had gotten negative 9/13 when we plugged that in as our slope, and there it is in its decimal form, negative 9 over 13. When we look at it in its expanded decimal form, it's giving it to me there in Desmos down at the m of a b right here. All right, so it's kind of it's nice to have a visual, and we can see these curves. While they're not easy to write explicitly, right? We'd have to split this up into actually multiple pieces in order to write this explicitly as y is a function of x, but we can do it implicitly now, all the same things that we did before. Okay, to wrap out this video, what I want to do is I want to do one last example where we actually look at a second derivative. So we've talked about finding the derivative dy dx, but how do I take a second derivative? Well, I take a second derivative by taking the derivative of the first derivative. So taking repeated derivatives to get higher order derivatives. And so let's do some practice with one where we do it implicitly. So here we've got x squared plus y squared equals 1. That is just a circle, and actually in the first video we did a similar one, except I think it was equal to 4 instead of 1. So this is a circle, radius 1, and we want to find the second derivative. So this is a circle, just if we wanted a visual, this is a circle with a radius of 1. Okay, so if we want a second derivative, that's what this means. That says a second derivative. If we want a second derivative, we have to start by finding the first derivative. So how do we find the first derivative of something where it's either difficult or impossible to write it explicitly, or it isn't given to us explicitly, y is a function of x, or vice versa? We do it implicitly. And as we take the derivative, we remember we're thinking of y as a function of x. So we get right in here, derivative of x squared is 2x, derivative of y squared is 2y, but because y is a function of x, we also have to multiply by dy dx, and the other side, of course, is just 0. So as we solve for dy dx, so 2y dy dx equals negative 2x, and dy dx is equal to negative x over y. Okay, now I want a second derivative. So now I'm going to take the derivative. So now we're going to take the derivative of the derivative. So now we're going to take the derivative, I'm going to write it this way, the derivative operator of the derivative. So now we're actually going to take the second derivative. So taking the derivative of the derivative, I'm not going to write those in words, that's what that operator of dy dx means. So we're going to take the second derivative. Again, though, we're continuing to think of y as a function of x. We have to remember that. All right, so taking the derivative, the second derivative of y now with respect to x is going to be the derivative of negative x over y, but that's a quotient. So I have to apply a quotient rule. So as I apply quotient rule here, this is going to become the derivative of the top, which is negative 1 times y, minus the derivative of the bottom, which is 1 times dy dx, times the top, negative x, all over the bottom squared. So let's simplify the top. The top is going to be negative y plus x times dy dx, all over y squared. Now, that is my second derivative, but it's funky to leave it with that dy dx in it, especially because we know what dy dx is. So let's make that substitution. So now that I know what my second derivative is, it is written in terms of x, y, and the rate of change of y with respect to x, so we're going to make that substitution. So we'll get down here, and we're going to get negative y plus x times negative x over y squared, and simplifying that, I'm going to write that as 1 times 1 over y squared. So I have negative y minus x squared over y times 1 over y squared. And to simplify that further, I'm going to write that as negative y minus, let's actually make it all one fraction. So I'm going to write that as negative y squared minus x squared over y cubed. And that is my second derivative of y with respect to x. I left off my with respect to x 2 times. Somehow I left that off up there. Okay, so we're taking the derivative with respect to x both times. So we need that 2 right there. All right, and we've got it. Okay, and if I wanted a third derivative, right, I could keep this going. If I wanted the third derivative of y with respect to x all 3 times, right, then I would just take the derivative, and I'm not going to do this, our video is getting a little long here, but I would just take the derivative of the second derivative, and I would dot, dot, dot. So we could keep going, remembering that we have dy dx, and the way we get to higher order derivatives is we simply take the derivative of the derivative.